The next topic we're going to look at is what is called oscillation. Now, an oscillation in general is any repetitive motion, but we're going to look at simple harmonic motion, which is a special oscillation, one that obeys certain principles that we will discuss shortly. We'll start out by studying a box connected to a spring, and we will assume that there's no friction whatsoever, none on the table, none internal to the spring or anything like that. So once we stretch this box, stretch the spring out and let go of the box, it's just going to oscillate back and forth forever unless something stops it. And this is an example of simple harmonic motion. And so we will look at some of the equations involved that will help us identify other cases of simple harmonic motion. We'll start out with Newton's second law, F equals ma. And if you're at the middle here, there's no force and no acceleration, so that's not very interesting here. But if we displace it a little bit, we get a spring force that's equal to negative kx according to Hooke's law. And we can rewrite the acceleration as the second derivative of the position with respect to time. First derivative is velocity, second derivative is acceleration. Then I'm going to go ahead and divide both sides by the mass here just to get both of my constants together and get them away from there. Rearrange things a little bit, and this is actually my equation for simple harmonic motion. Whenever you have some system that gives you an equation of this form, you know that that system will undergo simple harmonic oscillations. You might have different constants here depending on what you're dealing with, but in this case we have a k and an m. Now to solve this is a second order differential equation. Gotta love the bell ringing. And differential equations isn't a prereq for this course, so we're not going to go through the full solution. Turns out the general solution for this is a times sine of omega t, where omega is just the frequency in radians per second, or the angular frequency, times b of cosine of omega t, where a and b here are constants that depend on the physical situation you're looking at. There are a variety of solutions. A sine by itself or a cosine by itself can be solutions to this equation. And if we think about what's going on with the motion of this block back and forth, if you imagine we're looking at the bird's eye view now, and this block is oscillating back and forth, and if you have some paper scrolling by, like a seismograph or something, you might imagine that tracing out a nice curve. In this case, if you have time start when you compress this thing and let it go, then you would want a cosine instead of a sine, or some combination of sines and cosines. So let's assume that we can describe the position as a function of time. In this picture, the up and down position. In the other picture, the left and right position. As a cosine of some wave of some amplitude. So we'll have a times cosine. Omega, again, is our frequency, times t. And just to make it more general, in case we didn't start right at the peak there, we can add a phi here, what's called your phase angle, that can basically adjust for starting at different locations. Now, if we assume that this is a solution to this equation, what we can do is just plug it in and check. So we need the second derivative of this guy. So the first derivative is going to give us a negative omega, because that comes out of there. A times sine omega t plus phi. And then the second derivative is going to give us another omega out here. So omega squared a, and then we're back to cosine omega t plus phi. So if we go to plug this in, then we've got negative omega squared a cosine omega t plus phi. So that guy here was just the first term in my equation, plus this guy here, k over m times that guy. So omega t plus phi, and all of that has got to equal 0. So if we factor out the cosine here, then we're going to get k over m minus omega squared a, all of that times cosine omega t plus phi. Oh, I forgot, there should have been an a here, so we're going to pull that a out, get rid of that guy. Okay, so all of this has to equal 0 if this is actually a solution to that differential equation. Well, cosine is 0 sometimes, but not all the time, so that's not good. We can set a equal to 0, but that's not a very exciting oscillation if it's not moving. So we could say that this term here has to equal 0. And so if we have k over m minus omega squared is equal to 0, that tells us that this is indeed a solution as long as omega equals the square root of k over m, which it indeed does. Experiment will show that. So here is our solution for our wave equation. And once we have this equation, we can get one for frequency, because frequency is omega over 2 pi. So frequency is just going to be 1 over 2 pi times root k on m. And we can also get one for the period. So all the same terms we used for circular motion or wave motion, if you remember that from last year, apply to oscillations as well. The period is 1 over the frequency, so that is going to be, running out of space here, I'll just write it down here, 2 pi times root m over k. So these are some important equations you should have written down for your toolbox, so to speak. Okay, so let's look at a bit more closely what's going on with all of these things. If this is our cosine function, x equals a cosine omega t plus phi, then our displacement as a function of time is just going to be a cosine wave. Our velocity as a function of time is the derivative, which we took earlier, right? So negative omega times a, so this is going to be a sine wave with a negative, so it's upside down, right? Omega t plus phi. And then our acceleration is going to be negative omega squared a cosine omega t plus phi. So it will look like this, but a mirror image. And if you think about this going back and forth, here when you're passing through the equilibrium point, that's when your displacement is going to be 0, so that corresponds to here. That's when you're moving the fastest, so you're going to have the maximum velocity there. It's also when there's no force acting on it, so that's when you have the minimum acceleration, and you can do that for any point along these things. Now what about this phi? What if I didn't start right here? If I started with it initially at the equilibrium position and at rest, and rather than pulling it and letting it go from at rest, if I just gave it a kick right here, well, in that case, instead of starting with 0 velocity, I'm going to start with some velocity up here, and it's going to flip all my sines and my cosines, because I'm going to start here at 0, and I'm going to go up. Let's see, it's got to have the same period of t, so I got to be going down and back, something like, yeah, you get the idea. All right, so this phi allows you to adjust for those initial conditions. Let me jump over. If we look at a sine wave here, now I made it y equals, because if I did x equals, it would go this way. Omega is our frequency, so we can adjust that, and that just obviously adjusts how close together our crests and troughs are. Here is our phase, what we call phi. Right now I've got it just as the cosine function, but if I started with some different initial velocity instead of 0, then that's just going to shift the initial position of my wave. But it doesn't really change the fundamental physics that's going on. It just changes what we call the initial position, or the initial conditions, sorry. All right, now we can go ahead and look at the vertical case. Pen got changed color there. If we've got a vertical case, it actually works out kind of nicely. So if we imagine a spring at equilibrium, and then we hang a mass on it here such that it stretches down a little bit, and we let it settle in so it's not bouncing up and down, then at that point you've got the spring force, so kx naught, because we're saying this is a distance x naught, is equal to the gravitational force. And then if we do the sum of the forces equals ma again, you're going to have negative kx, where this is any x at any location, not necessarily right here, plus mg equals ma. In this case, we're taking down to be positive. And then we can substitute in here kx naught for mg, so we'll have negative kx plus kx naught equals ma. And we can factor out the k, or actually a negative k, and then we'll make this just a delta x, which is going to be the difference between those two x's. And this is the exact same equation we had previously. So you can use all the same equations for box bouncing up and down on a spring vertically that we did for the box sliding sideways, as long as we reset our equilibrium position, as long as we understand that this x in the equation now and our x as a function of time being a cosine blah blah blah, as long as all of that is with reference to the new equilibrium position of x naught here. Okay, let's do a couple of examples here. We've got a loudspeaker that has a cone in simple harmonic motion, so that means it obeys all of these equations that we just derived. And that's the frequency. We know that this is the amplitude, and we're defining at t equals 0 to be at maximum displacement. And we want to know the equation that describes the motion at the center and velocity and acceleration as a function of time, all of these wonderful things. So what information do we have? Well, we know that the frequency is 262 hertz, and we know that the amplitude is 1.5 times 10 to the negative fourth meters, and we know that at t equals 0, x equals a. So that's just setting our initial conditions. That essentially tells us that we can use the cosine version of the equation. All right, so for part A, we want to know the equation of motion, so we're going to use the cosine version. If we would say that t equals 0 when you're in the middle, when x equals 0, then you would want to use the sine version of the equation instead of the cosine version. But anyway, x equals a cosine omega t plus phi. This tells us that phi equals 0. This condition here tells us that our phase angle is equal to 0, so we can just have a pure cosine wave for this. And then we just need to plug in our information. So we've got our amplitude, 1.5 times 10 to the negative fourth meters times cosine. Now omega is 2 pi times the frequency, so 2 pi times 262 times time. It's still a function of time, and there is how you could describe the position, the displacement of the speaker as a function of time. And for part B, we want the velocity and acceleration as a function of time. So velocity again was just negative omega a sine omega t. So you just plug in the numbers. I won't even waste your time. And then we also want acceleration, which is negative omega squared a cosine omega t. And we've got all these values, right? So we can just go ahead and plug those in. For omega here, again, you'll want 2 pi times 262 for those. Oh, I forgot to point out earlier that if you want the maximum velocity, that occurs when the sine part of your equation is equal to 1. So the maximum velocity you'll get is negative omega times your amplitude. And if you're just interested in the magnitude of it, then you can forget about the negative. And the maximum acceleration is going to occur when the cosine function is equal to 1. And so you'll just get negative omega squared a. And if you substitute in the first expression we had, that omega was equal to root k over m, then you'll get this is equal to negative root k over m times a. And this here is just k over m times a. Usually we don't even worry about the negative signs because we just want to know the magnitude of the maximum of these things. All right, part C, we want to know the position of the cone at 1 millisecond. So we're just going to plug in that for t here. I guess I'll go ahead and write it out because you like watching me write stuff, right? Right, okay. Cosine 2 pi times 262 times 0.001 This has got to be in radians, by the way, so make sure your calculator's in radians if you're using omega. Plug all that in and you'll get negative 1.13 meters is the location. One other example to do, a whole bunch of things to calculate about a spring. So we've got a spring and it stretches a bit when we put a mass on it, and that's going to help us know the spring constant. Then we set it up horizontally and give it a push, and no, we pull it, sorry, and then release it from rest. We got to determine all of these things. Okay, spring constant, we can use F equals kx for this. And so k equals F over x. F is going to be gravity on this, so mg over x, so 0.3 times 9.8 divided by the amount it stretched, 0.15, and that works out to be 19.6 newtons per meter is our spring constant. Then we want to find omega. Once we have the spring constant, omega is easy, it's just k over m. So root 19.6 over the mass here, 0.3, and that works out to be approximately 8.08 radians per second is the angular frequency of this thing. The amplitude, well, if we stretch this thing, oh, it didn't stretch it, we compressed it. Anyway, we compress it and then let it go, then that is the maximum displacement, so that is also equal to our amplitude, so 0.100 meters. That one was tricky. Okay, maximum velocity, so I just mentioned in that previous slide that you can find that by doing omega times a, and that gives us V max. And we've got omega, 8.08 times a, which is 0.1, so we get 0.808 meters per second. Maximum acceleration, omega squared a, 8.08 squared times 0.1, and that comes out to be 6.53 meters per second squared. Cruising right through all this stuff. Period and frequency, it's easier to find the frequency first because it's omega over 2 pi, and that works out to be let's see, 1.29 hertz. Once you have the frequency, you can find the period by taking the inverse of that. It comes out to be 0.777 seconds. Displacement as a function of time. So once again, we didn't give it a kick. We pulled it or pushed it and then let go. So we're going to have x equal to a cosine omega t again. In this case, a is 0.1 times cosine of omega, which was 8.08 times t. And there we go. If we want to find the velocity at 0.15 seconds, first we need velocity as a function of time, which is going to be a omega sine omega t. And then we just plug everything in. We've got a, we've got omega, we plug in that for our time, and we end up with 0.756 as our meters per second here. Let's see, I think I forgot a negative sign here, so that would make that negative as well. But there you have it, all kinds of fun calculations we can do. Okay, thanks.